Okay, whatever. Then I'll just have it without music, I guess, or can I still add it? Um, no, you know what? I'm just gonna leave it. So, um, I want to implement this paper that just came out a few days ago from Bain Capital Crypto called ZODA, Zero Overhead Data Availability. It's really cool. Um, haven't seen any code for it yet, so I want to implement it. Now, I know that the Celestia team tried to do some benchmarking and they couldn't. And that was just due to some like technicalities with the libraries that were available in Golang and compatible with Celestia specific libraries like the 2D Reed Solomon encoding one. But in Rust, we don't have that. Um, eventually it will have to be made, but like I just wanted to do a very abstract implementation of ZODA that operates directly over these field elements instead of taking in bytes. And then yeah, so that's it. I think I would start by figuring out what the hell they're doing. Like I already started a little Rust implementation that I'm gonna go into and improve and like walk through, probably rewrite from scratch on the stream. But I think it'd be helpful to first like kind of draw it out or do some explainers. So for that, I have this scene here. Where's my keyboard? How do I lose my keyboard? There it is. Um, so we have something called a data square. Let's see here. What happened to my output? Okay, there it is. So we have a data square. I don't like the shape of this. Let's say it's black. Um, and now you can think of this just as like a vector of data that gets split up into multiple rows. The reasons for that are there's a few that I'll probably end up having to explain. But you just reshape your array of bytes. That's a gross simplification, but you reshape your vector of bytes into a square, and it has to be a square. And then we have, let's see if I can do this in a way that makes sense. What am I doing? It's not what I wanted. So, um, let's say you end up having 4 rows and 4 columns. Um, let me kind of reposition these. And so obviously these elements are not like single bytes. What we call them in Celestia are shares. Um, and shares are 512 bytes, but that doesn't really matter here. What's important is that we split up the bytes into this square type data structure, and then we um, do Reed Solomon encoding on it, which is a type of mechanism, I guess, where you can recover data from either the extended bits or the original or any combination of such. So like, let's say I should probably learn the shortcuts for this Excalibur. Um, but let's say, wait 1 moment. I also gotta check my do not disturb. It's on. Um, so we have the square and then we extend it and then we get a second square. So now we have a rectangle. Great. What does that do for us? Not much. But then we can sample this data. Well, let me finish all the steps first because otherwise it's going to get confusing. So first of all, we can look in this at like on two different axes, right? We can look at it row by row or column by column. So you can interpret this column as a row and then extend it in the same way. Let's see if I can copy this. And then we have this. And then I forget which way it's done in. I believe in Celestia we just encode this out, but it could also be from here down, one of those two. Um, but anyways, we end up with an amount of data that is 4 times the original, and then light nodes come in and they sample like individual squares here. So like you just pick, let's say, two random coordinates, okay, and then another light node comes in, samples two random coordinates, blah blah. Another light node comes, samples another two, and eventually, if you have enough light nodes, you have some security guarantee that because the light nodes can also share this data that they've sampled with each other, that the entirety of the data can be recoverable, um, or that it's not being, the original data is not being withheld. Um, and so there's an issue with this, um, and that is that it requires fraud proofs to work because maybe my light node can sample two shares, but I have no idea if this was encoded correctly, dude. Like from the Reed Solomon side, I'm just getting some bytes, and so there needs to be full nodes that are also doing this encoding procedure, and then being able to, let me think, notice, oh hey, the guy that did the block producer didn't do this encoding correctly. Here's what I mean. And then they take the part that they found that was done incorrectly, or like a single one of them, and then they can give just this column to a light node along with the fraud proof. So that's the main reason, one of the main reasons we split things up into 2D. It's because if you had a single byte vector and then you want to prove that you encoded, like, let's say this first half correctly, and then another full node sees that you didn't encode it correctly, then you're going to need to send light nodes the entire block for them to verify the fraud proof that um, that you've been defrauded. So that's not that cool. It makes a lot of sense for Celestia to do this, and of course, like when designing Celestia, the big brains knew, they chose very deliberately to go the path of fraud proofs over validity proofs because um, KZG commitments were and are so expensive and not really that easily scalable. But I don't know much about what I'm talking about when it comes to that right now because I have not spent enough time looking at the uh, alternatives or the alternate solutions. But the ZODA thing is pretty cool. So what we do with ZODA, now they explain it in a very mathematical way, which I'm not going to do because they have to formalize it, of course, because it's a paper. But they say, okay, well, instead of doing this, okay, we're going to extend the extended data and whatever. They first, all they do is they, let me just delete these. They first read Solomon encode the columns. So then they call this like original matrix x hat. I don't really have a pen. Let me see. Maybe I should just use the pen. Okay, x or something like that. Is that what they use? Let's check the paper. Um, Let me find myself. Oh, I'm gonna have to go plug in my charger. Forgot about that. Yeah. And then they say that you get this X by multiplying the X hat matrix with G, the G matrix, which is the encoding matrix. In practice, it's like this matrix is just a formalization. Like we're just read column encoding column by column. At least as far as I understand. Maybe I'm also just saying things that are incorrect, but um, and then we get the, I think they call it X. But then here's where they do something interesting. They throw this data with the extended data together and they Merkleize it. So then we have some tree. Let me not put it there maybe. Um, so there's some tree where this data lives. And it includes the extended data. Let's just say, for sake of simplicity, that the original data is here and the extended data is over here. That means you get a Merkle root, uh, whose value is dependent on the correct encoding of the data. And then you can use this as entropy for randomness and constructing the rest of the uh, extended data. So first of all, I should probably open my, 1 second, I need to check something. My restream so that I can see a chat if I have it. My screen is invisible. No audio. It's over. Wait, let me check. Empty whiteboard. Oh, that's very strange. I have no idea why it wasn't streaming that. Let me see. What does it look like on Twitter? All right, well, thank you for pointing that out. Ha! Uh, Alrighty, thanks. Okay, so I guess I'm going to skip Excalibur because what the hell? I don't like that. Um, that's fine, I guess. Let me move this over to another window though so that I can actually see when people are commenting because that sucks a lot. I think the right way to go though is to then just take a look at the explainers and then I'll jump into the code. Oh, I know what happened. My monitor reset or something, and now my screen capture is borked. Let me try to. There we go. All right. So we should be fine now, I think. Let me go back a little bit. Yeah, let me kind of rehash what I said. So this is the way Celestia normally works. We have the original data. We just do a read column encoding, like downwards if you look at the columns, and across if you look at the rows. By the way, if you can see this, please say something. No, I'm echoing like crazy. I know why. Does that fix the echo? Please tell me it fixes the echo. What a disaster. Okay, Echo's fixed. So, we have this original data. We read Solomon encoded downwards and across. And then either from here, we extend one more time, and then you end up needing fraud proofs because um, you can't be sure that the data was encoded correctly because it's not like put into these little parts that light node sample. So what ZODA does is ZODA first encodes normally like we do, but then it puts it into a Merkle tree, and then it uses the root of that Merkle tree as entropy, and I think that's where I left off. So, like on the math, like they're doing it all with linear algebra, but uh, basically you just take this root, and then like let's say we have four rows, four columns here, then we're gonna generate using this like Merkle root as a seed for entropy, four field elements, um, four random field elements from the field. So like let's say they're A, B, C, D, and then what we can do is we can multiply. Um, let's say first you multiply this vector by A, and then this one by B, this one by C, this one by D, and then you do the Reed-Solomon encoding. Then you have a square where you can actually verify that the encoding was done correctly. Because you can generate this Merkle tree if you have the hashes already of the individual rows and columns. And the same is done here, you would just multiply these rows by A, B, C, D, and you get that data back out. All right, so cool. I think it might make sense to look in the paper. Um, like I said, so this is normal Celestia. You sample a ton of squares individually, and then you need to get a fraud proof to prove that something was not encoded correctly. And then with ZODA, you have this encoder matrix G, and what that really means is just encode the columns. And then you generate this diagonal matrix, um, where on the diagonal you have those elements I was talking about. So in this case, it would also be four. Um, and then after that, you are uh, applying the encoder matrix to it. Now it's transposed here because you're no longer like encoding by column, but you want to encode by row. So you transpose the coding matrix and then you're good. And the same thing happens here. So you first do columns and then you go across. Um, so yeah, let's do it. I think if I, where would my Z be? Here it is. Okay, so I already started a little bit, but it's very crude, and I think I kind of want to redo it because it was very lazily done. Um, so let's see here. So what I have is I'm using this Binius library. It's for snarks. It's pretty cool, but they have Reed-Solomon encoding and the Merkle tree I need. And most importantly, we can do operations on a 128-bit field, which we need for the security. So the Golang library is only over 8 and 16 bits. Um, but yeah, this is okay. So this is all I wrote. It's not that much. Well, I started out by trying to rewrite RSNT2D in Rust, and then I realized like, no, like let's just get ZODA working. And then maybe we can come back come back around to that. But here I have a data square that has an encoder and then it has the rows, and then a field element would be considered, I guess, like a share in Celestia. But so we would have to split up the 512 byte share into these field elements to be able to operate on them. And then the Merkle tree that we end up creating is also over, where is it? Is exactly over those field bits. Now, why is this complaining? Type mismatch. I'll get around to that. This is obviously laziness. So I think um, what makes most sense is that I'm going to talk through it and then probably just comment out all the code. Um, there are some nuances here, like not nuances, but some things I did strangely. Like for example, I started out by doing it by row and not by column, like in ZODA. But I think it's going to be easier to test if I just do it straight up by column. Then another thing is that I'm using the like native Merkle tree implementation from this crate, but I'm not sure yet if I can. I mean, of course in theory it should be just as easy to build it from the root and column hashes, but I haven't tried that yet. I think the verification code is really going to actually be the difficult part, in getting these crates to work together well. Um, so first thing I do is like let's say that this already contains the uh, original data. Then I just we loop through the rows, and the encoder has something that says encode in place, which takes immutable reference to the extended row, and then I push that onto this two-dimensional vector of the binary fields. So um, what we really need to do is do that by columns, and that's really easy because we don't have any initialization code or anything yet. Also, I don't even think I'm using this anywhere. Right? No. So I'm going to. Does that work? Okay. Um, I'm wondering if I should even do that first, because eventually what I do, okay, so then I build this tree, and then first of all, I don't even put the elements in there because there's some Rust problem with the type that is contained in the vector not being able to collect after flattening it. So I'm throwing in a empty vector for now. And you seed the RNG with it. And I don't think that this is what is meant in the paper by using it as entropy. Um, I'm assuming what we really need to do is like uh, just generate a hash. Um, like let's say we have ABCD, you can concatenate the digest with 1, 2, 3, or 4, or like XOR it or something, and then hash that, and then interpret that as a 128-bit UN. Oh, okay. Nash Q, one of the original researchers on this, is still awake. Okay. It's old, old. I wonder why Restream is showing something so old. Is it even cut up? I hope it's cut up. I'm actually gonna check. Okay. Seems like we're fine. Excellent. Beautiful. Uh, so, how can you join? Do you want to join the call? Like, should I set it up? All right. Good question. I don't know. How do you want to do that? I guess I could set up a Google Meet, and then I have to fix my streaming audio. Um, so give me a second. I need to. Okay, I'm gonna be echoing for a second, I think. Let me turn off that music. Am I echoing? Oh, I have to be. That looks annoying. But now? Now it should be fine. I think it's fine now. It's not trouble, don't worry. It's not, like nobody's watching anyways. It'll be people watching the recording if anything. Okay. Well, I guess if anybody wants to join the call, wait, that's a bad idea. I'll just telegraph it to you. You can still hear me, right? Oh, that's running. I have to get my charger anyway. Oh, my coffee. I forgot my coffee.
Jim.
I'm hearing your audio through my computer instead of through the headphones, which is not that great.
Okay.
Wait, never mind. I think it's fine. Say something?
Yeah.
Okay, yeah, we're good. Hello, can you hear yourself on the stream? We need to figure that out.
Uh, Let me check that.
Okay.
How can I check that without doing an echo?
I don't think you.
Uh,
Oh, you're loud.
yeah, I'm on the screen.
Okay,
But I am loud.
you are loud. Okay, so, um,
Where yeah,
I have some. Where am I at on the code?
yeah, yeah. I just joined. I have no idea, no context.
Okay, so I tried doing an explainer on Excalidraw only to find out. Okay, now I think it's working again. So code-wise, we have um, this. This is it, and it's really bad. And I'm doing it first of all, rows first, which I guess is it's not really that big of a deal. Oh, what happened there? I'm doing it row by rows first, and then things kind of just got out of hand with this, like seeding from the value, casting it down to a U64. Like it's obviously not correct, right? So I was just explaining that I'm pretty sure what we're supposed to do is like XOR the root with like I don't know some counter and then hash it and interpret that hash as a field element. And that's what I mean
Mm,
by entropy.
you can do that,
Can you turn down your
but you
mic
can
slightly?
also.
I don't
I,
know
how
if it's possible.
am I too?
You're a bit loud. Hold on. I don't want to fiddle with it. It's probably fine.
I am too loud.
I think it's fine. Maybe I
Can I
just needed.
whisper?
No, no. I think it's fine now. I think I fixed it. I think it was just on my end, the my headphone output. Okay.
Okay.
Um. So yeah,
Well,
what is mint?
the simple thing is you hash two values, and but I think you can also XOR. It should be fine.
Yeah, true. I could just concatenate them. I don't know why XOR can.
No, but
That
it's
was
true. But like, no,
over-engineered.
it's true. The XOR of one random number with another number is still a random number. So
The entropy
you're
is the same.
saving on a hash. I don't know what's more efficient. Do the XOR of the
Yeah,
hash.
that's. Yeah. Anyways, so then I generate my vector, and then I just make so many random field elements as there are rows in the original um, data matrix. This is obviously like I need to handle width better. Um, and then I want to, because I first extended by row, I then needed to multiply the columns by the elements in DR. So that's why I then start looping through them as columns. Um,
Why do
well,
you?
this is
For
reshaping.
what
This is
reason? About
because
like.
there's an experiment before I wanted to code. This is my prototype before the stream. So just like proof
No,
of
I'm
concept.
saying like, why did you start with the rows, not the columns?
I don't know, brother.
Okay.
I was kind of just I don't know. I think it was just because when I was actually like trying to rewrite RSMT2D, I had it by
Yeah.
like row column first, and
Mm.
then I realized,
Oh my God, this will make it so confusing.
yeah, so that's what I was saying. I said before you came on that I want to change it now into columns because I know that during testing this is gonna bite me in the ass.
Yeah. Okay,
So that's one thing I want to do. Um,
we can do that.
there are like other problems. Like I don't know if this is correct. It should be. This is then
You're still
after
using
I
the.
decompose the matrix. Um, I multiply and then encode.
Okay. Are you are you taking the full matrix and then multiplying it by this diagonal vector, or are you
I'm not
doing
doing any.
row?
No. This is what I'm doing. I'll explain to you in Algebra. What I'm
Okay.
doing is I'm saying, okay, first I take my square. You know, I'm not gonna. So first,
Let me open you up on Twitch to have a little less delay.
oh wait, how about I screen share on the Meet too? I wonder if I can.
That's on my phone.
Oh,
That's fine.
okay. So I have this square. Let's say it's a very uneven square, very lopsided square. But um, first we encode read Solomon code like normal, downwards. This is what I meant when I said G is just a psyop. There is no encoder matrix. You just it's just a formalization. Because this is already x is g x hat, right? And this is equal to x hat. Okay, do you
You
see?
next ZODA.
Yeah, whatever. And then so then what I do is we put it in a Merkle tree. Okay. And then we have a root. And that root is already a field element. So and then I use that as entropy to create four more field elements. Let's say A, B, C, D are all inside my field. Okay? I can even. I feel like I'm
Multiply.
back in university now.
Can you send me a Twitch link? I can't find it.
Oh, what link?
Your Twitch link.
Oh, brother. Yeah. You can also just look on Twitter. It's probably just as fast on
No,
Twitter.
I'm looking on Twitter, but you just wrote F.
Oh. Um. Wonder if that's faster. It's probably not much faster. There is like this is not zero overhead streaming. So
You should do a hand sign or something.
all right.
Yeah.
Wait, let me open
Write something so I can see the latency.
that. Okay. Ready? I'm gonna write something. Three, two, one, draw. It's taking that long.
I got it on Twitch. Yeah, it's faster than Twitter.
Okay.
Yeah.
So
Yeah, I'll just.
yeah, go back to Twitter.
Yeah.
Anyway,
Twitter
so
is faster.
I
Yeah.
generate these like four elements. Now I'm not putting them
Yeah.
into technically I am putting them into a vector. Okay, so it's in a vector.
Yeah.
But I'm not doing like I'm not using any matrix APIs or anything. I'm then just saying, okay, well this times A times B times C, like an element wise multiplication. That's what's meant, right? By multiplying the vector. If you have a diagonal matrix, right? So if I have A, B, C,
Wait, no. There is a like think of it as an actual diagonal matrix where A is in 1 1, B is in 2 2, C is in
oh,
3
the
3.
one, yeah, yeah, I know.
Oh, yeah, sorry.
Yeah, but okay,
Yeah.
exactly. And
No.
so if I then multiplying it with yeah,
Yeah, you're doing correctly.
yeah,
Uh,
okay. You made me second guess myself. I got nervous for a second.
no. I'm just looking for the delay. I just
Okay.
saw the ABCD be written next to
Yeah.
X tilde, and I was worried how you multiply.
Okay. Yeah, yeah, yeah. And so then and then I encode after that. So that's just like,
Wait, can you like the multiplication of how do you do the multiplication of
encode right now? It's a joke. Encode right
no
now.
no
Let's say for
no I
each
mean
mole.
the the like what is this ABCD row next to the
Oh,
X
that's just
tilde?
that's my. I'm saying like if you look at it by row, right?
Yeah.
So this is the A row, this is the B row, this is the C row. So I'm multiplying everything in that row by B because it's the second element. Like from
No.
should it
Let me
be A B
understand.
C D? Should I be multiplying A B C D on every? Oh yeah.
So
How does the verification work if I just?
no. Like Do you remember how to do diagonal multiplication?
No, hell no.
Okay, so an easy way to remember that is write this ABCD matrix on the top right
So it's
next to x tilde, above x tilde, but to the right. And then you see where the things meet.
right. So is it like this? Like first, does it end up being this?
Yeah.
Okay.
So it's gonna
Down
be
here as well.
it's going to be yeah, exactly.
Okay. That of course gets extended the same way.
No. Well, like you're now drawing
Well, my
y.
drawing is like obviously incorrect, but you understand with context what
Yeah.
I'm saying. Okay. Okay.
Yeah.
With context, it's fine.
So okay, well, okay. Think of it. How you can do it row wise, right? The multiplication,
Why?
which is just what?
What do you mean?
It's a well, it depends on how, like what's more efficient, honestly.
We're just trying to make a prototype. We just want to get the thing
Yeah.
going. So,
So like you don't have to create the diagonal matrix. Is what I'm saying.
and yeah,
Right.
I don't.
Yeah.
I don't. I have a vector.
Yeah. So if you take a row and then multiply it, like do an inner product with the vector of the
Yeah, just
the functions, right? You will
multiply.
like you take the first element of the row times A, then the second element times B, times the third element times C. You get the row of diagonal times X.
Brother, if I have a row,
Yeah.
X, Y, W, Z. That's very strange, W. X, Y. Only Z is there because I forgot to put W at the beginning. And then we have A, B, C, D. So this is my field element vector. So this is like whatever, D, R. And this is from X.
Remember, I have a little bit of a delay. Okay. Yeah. So you have X, Y, Z, W, Z, and A, B, C, D. Yeah.
Yeah. So if you do X dot zip dr.
Yeah.
And then you have XA.
Nice. Okay. Yeah.
So that's fine. That's probably what I'll do. Okay. So I think the first thing we need to do is like, can you read Rust pretty fine? Or should I?
Yeah, it's fine. It's just code red.
Yeah. You do the important work of idea guying.